Okay, we're in section 22 of the notes. It's the linear approximation differentials. Certainly, as always, not always, as always, but we do try to do a lot of visuals in the classroom. We'll give you some visuals. I'll go through these at the whiteboard later. But for the most part, we're looking at a curve with tangent lines, and you should be able to appreciate the tangent lines are fairly good approximations to the curve within a region. Now, sometimes a region is very small area, region of approximation, so it's much wider. All right, we'll talk about that in a little detail as well. So we'll go through some, first page, we'll do that, about the tangent lines and how they approximate the curves pretty nicely at the point that they're tangent to. We'll talk about a linearization, that is the equation of a tangent line, essentially. Excuse me. We will talk about using a linearization to do approximations to functions near the point of tangency. And we'll go through examples of that. Then we'll talk about a concept of differentials related to derivatives, but different. And for the most part, if you don't take a derivative, you can certainly take a differential, and we'll go through that. We'll write down what it is, and then we'll go through examples of that. We'll talk about how to use that to approximate things like delta F, and delta F is usually a pretty difficult thing to approximate, but using differentials, it's a little bit easier to approximate it. Again, we'll go through examples, and then we'll go to the real examples. So we're going to introduce topics, and then we'll go to do the examples next. So let me go to the whiteboard. And as I do that, I'm going to talk through each part of the notes. And I want to encourage you, as I do this over here, you should start to think to yourself, is this the way I should read notes? It is. When you're reading a textbook, you should be reading a textbook with paper and pencil, and you try to understand what they're trying to present to you. All right, give me a second. Share the screen with you, right? All right, so let's look at this first up. And, they say a visual approach. And I want to be honest with you, visual approach is really something we've done in the past, by the way. And with the graphs we've seen so far, well, this is a graph, right? It says the graph we've seen so far, except the sharp corners, can be local linearized. Yeah, we've done that before. So, for example, we've been using the tangent lines for a while, and we have. So I'm going to say tangent lines are good fits in a local neighborhood. Here's the sine curve. So I want to point out what they're giving me over here is a sine curve. This is y equals sine. And they tell me they've got a point of tangency here. And the point of tangency here is going to be the point, I'll write this down for you, pi over 3. And pi over 3 is going to be, for the sine, would be root 3 over 2. Let me just see if I did that right. Pi over 3 is, let's see, 60 degrees, right? And 60 degrees will give you a ratio for sine. Yeah, it looks pretty good. All right, and they give another point of tangency to this curve over here, and they say the point 0, 0. All right, what I want to do is I want to write the derivative for sine down to dy dx. We've done this many times before, is cosine x. So what's m tangent here? Well, m tangent there would be 1/2. Why is that? The cosine evaluated pi over 3 is 1/2. What's m tan here? Well, what's cosine of 0? It's 1. So let me write this down. I'm going to put the blue curve down first, line, I should say. What's it going to be? Y minus, right? Just a linearization now. The y coordinate, which is root 3 over 2, equals, what's the slope there? 1/2 x minus pi over 3. All right, let's do the red line. That's the red line here. That's going to be y minus 0 equals, the slope is 1, x minus 0. All right. Now, what I want you to do is look at those two lines. I'm going to blow this up for you. And which one fits the curve better? I hope you're looking at and seeing the red line definitely fits a wider band. Like if you look at the blue line, I'm going to say within this region over here, there appears to be a pretty good fit. But if you look at this one over here, I mean, it's a much larger region, right? Much larger. fit region. So I'm going to say not all tangent lines are going to be equal in their approximating ability, right? Depending where you are, it's not bad if you're close to the point of tangency, but once you start to move away from that, it can get pretty bad, all right? But anyway, what I did over here was I zoomed in using the same scale, and I want to point out over here, this is that tangent line that goes through the origin and the sine function graph. And this is really the same scale being used over here. And I hope you realize that one fits better than the other. And that's really important. You know that. All right. So that's page number 311. We just finished that out. And I'm going to go to the next page and see if I can figure this one out. Now, by the way, this over here, someone's like, what the hell is this thing over here? And what they're basically saying is that the function is approximately the same. That's what that means over there. F of A plus F prime A x minus A. Let me go through that, tell you where that's coming from. So they're going to take a function over here. I'm sorry, let me go back to my pen. They're going to take a point of tangency. That point of tangency is going to be A, F of A. This is going to be F of X. M is going to be F prime at A. I can put the tangent line in, something like this over here. I know I'm not doing a great job of doing that. Let me write down a tangent line for you. Give me 1 second. What's it going to be? Well, I think I can do it, right? So it's Y minus F of A. Again, this is the equation of the tangent line. At that point, equals F prime of A times, let's see, what's going to be X minus A, right? Well, let's solve for Y, which is typically what you did in lower level courses. So what would be F of A? Let's see, plus F prime of A times X minus A. Well, what are we saying? We're saying if we're near A, that's a rather influenced term, by the way. If we're near A, we're going to say Y is approximately the same thing as F of X if we're near A. That's all I'm saying. So what do you get over here? Let's write that down. So Y is approximately F of X. Let me tell you where that is. That right over there. So let's take a look at an example. And someone says, you know, are you going to use a formula to do the example? I could. So I want to tell you what the example is going to be. And not that I always use the formula, because sometimes I say, so do I need to remember that? Not really. So I'll do it two ways. So the function's Y equals the root of X. Right, I'm reading this. And what they go on to say, they want to do this to approximate, they actually want an approximate of the square root of 15.57. I got to be honest with you, if someone asked me the square root of 15.57, I don't think I'd be using this method. All right, what would I do? Probably take a calculator out. But what I want to do is I want to just, I want to visualize it. And the square root function looks like this over here. That's what that looks like. This is F of X. Then I got to ask myself is, what point near 15.57 would be easy for me to do? Well, it's only the perfect squares. Let me write down the perfect squares that are easy for me to do. 1, 4, 9, 16, 25, yada, yada, yada. It's like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. I'm going to say 16 is going to be the easiest point to use that's nearest to 15.57. Now, someone says, well, I want to use 25 and see because I like 25. 25 is way far away from 15.57. You might say 9, it's still too far away. We want something near. So this is near 15.57. For example, they want the square root of 24.9. I would say 25 would be the near number. So let's put this down. We're not near 25, by the way. We're near 16. So what I'm going to do is I'm going to say, what's the point over here? 16 f of x is going to be the root of x, right? That's 4. Let's do the derivative. I want to write down the m tangent here. And what's m tangent? Let's write this down. It's going to be f prime of x. That's 1 over 2 root x. And f prime at 16 is going to be 1/8. So I can write down the equation of the tangent line here. What's that going to be? Y minus 4 equals the slope of the tangent line, which is 1/8, x minus 16. Hope I didn't go too fast with that. So what do you get over here? Y minus 4 equals 1/8 of an x minus 2. Y equals 1/8 of an x plus 2. All right, what am I saying? I'm sorry, this is the equation of tangent line to f of x equals root x at x equals 16. What am I saying? That this tangent line, when we're near 16, is actually looks just like the function. So I'm going to say f of x is approximately the same as 1/8 x plus 2. We are now going to use that to figure out approximately what the square root of 15.57 is. So f of 15.57 is the square root of 15.57 is approximately 1.8, I'm sorry, 1/8 15.57 plus 2. All right, I'm going to go to the computer now, and I'm going to do the computation for you. All right, so give me a second. I'll do a new share. I'm hoping you're taking notes, and when I look away, I'm looking at my notes when I do it. And let me open up my Sage, and I'm going to run Sage. I want to make sure you know what I'm doing over here. We're looking at, what example are we looking at? I guess we're looking at this example over here. So let me type in the square root. And again, I'm looking at my notes. So square root SQRT 15.57. And I get that number. And now what I'm going to do is my approximation, which is 1 divided by 8 star 15.57 plus 2. And let's see how close we are. So I'm going to say it's really not bad. We did a pretty good job. Now, do they differ? They differ. Do they differ by a lot? Well, that's relatively speaking hard to comprehend. But the bottom line is it's really not that bad. All right. So anyway, the actual square root of 15.57 is not known. But here's the deal. We can approximate it using a computer, and my computer came up with this approximate. If I were using the derivative, which I did, I'm getting this approximate. All right. Do they differ? Sure, they differ. Do they differ by a lot? Not a lot. So I'm going to put the difference down now. So square root SQRT 15.57. You know what? Normally, we're just not concerned about the direction of the difference. So I'm going to say the absolute value. And between f of x, let's see, minus, I'm just going to do a copy paste. All right, so I'm going to copy this. And let me paste that in now. Oh, I made a mistake somewhere. Oh, I forgot to close it out, I think. Where's my mistake? Oh, you know what? I got F written down, and it's not F. I'm sorry. I just spaced out. I'm sorry. ABS square root. Sorry about that. I thought I defined a function. I didn't define a function. Minus this thing over here. I just spaced out for a second there. And that's that number there. They differ by, tens, hundreds, 10,000s about 4/10,000ths in difference. That's incredible accuracy, right? So would you expect that? Of course you would. All right, let's go to the next thing up. I'm going to go back to the whiteboard now. And our goal here is to walk you through this notes as if you were reading them yourself. All right, so I did pretty good there. All right, so let's go to the next thing up. I got to do that for you, right? And let's take a look. Okay, so the basic idea, what we just did with local linearization is often used to introduce a new notation called differentials. Suppose y is a function of x where f is differentiable, then the differential dx is treated as an independent variable where we can write, well, you know what? This kind of reminds me of things we've done in the past. If you remember, dy dx equals f prime. I think you remember me doing that, right? But now we have this like new notation. We're saying dy, the differential dy, is equal to the derivative f prime of x dx. So let's take a look at an example. All right, let's see if we can write that down. So the example is going to be this over here. So y is a function of x. And what's that function? X e to the x. So the first thing I'd like to do is I'd like to just simply write down what f prime is. And what's f prime? It's dy dx. I've seen this many times before. How do I do that? A little complicated. I think I could do it though. Derivative of x is 1 times e to the x plus x times derivative of v to the x, which is e to the x. So dy dx, which again is f prime, is going to be e to the x times 1 plus x. Fairly simple to write that down. We've been doing that for a long, long time now. Now we write the differential down now. So dy is equal to f prime, which is e to the x, 1 plus x dx. All right, let's see how we did. See if they put that down. Well, I guess I didn't put it down. I got a next page. Wow, right over here. We did it. The only difference is I factor out e to the x, and they didn't do that. All right, let's go through this, which can be confusing at times for students. We're not trying to confuse you, though. All right, so I think we've seen notation in the past like this. And I want to point out, I don't think this is a stretch of your imagination at this point, but I am using symbols here that we don't normally use, and that's the delta x. It's something going back to Math 100. But I guess I should talk about that. So what does delta x mean? It means the difference in the x's. With the understanding that x2 is not equal to x1, otherwise we wouldn't have a delta x, would be nothing. All right, so x2 minus x1. What do we typically look at? Not that it has to be this way, but we look at a number line. This might be x1, this might be x2, and this here represents the delta x in a problem, which is upper minus lower x2 minus x1. All right. The next thing is the definition of the derivative at a, and we've been doing this for some time, and I hope you're at least familiar with that, although you may not be able to recall that. I want to point out Math 121, we generally don't use this definition. We use an alternative definition, but I want to point out its equivalent. So I'm going to write down a definition we normally write down, and let me do that for you. So f prime at a is the limit. This is the one we normally use, right? H goes to 0, f of a plus h minus f of a over h. The only difference is I'm using, instead of h, I'm using delta x. So really, there's not much of a difference there. It's the same thing. Now, of course, the next thing is the delta f. Now, I want to point out what the delta f is. This is actually the delta f in the problem. It's a change in the f. This is the delta f. Let's go back over here and just outline it for you. So this is the delta f. This, generally speaking, is incredibly hard to compute, but it can be done. I'm not saying it can't. But we're not concerned about the equality. We're concerned about the approximate equality. And what's it going to be? Well, the delta f is going to be approximately the same thing as f prime evaluated at a times the delta x. All right, let's go through that. All right. So I'm going to say, let's put this over here. So I'm going to put this over here. F prime of a, all right, is equal to the limit as delta x goes to 0. Let's write this down. It's going to be FA plus delta X. Just copying, by the way. I'm trying to show what I'm reading. And this is what I'd be doing if I were reading a textbook. I'd try to comprehend that. And I certainly know what delta F is. So I'm wondering about this thing over here and kind of looking at it. I'm going to say, if delta X is sufficiently small, so if delta X is sufficiently small, I'm just going to say small. It's kind of like an imprecise word. But I'm going to say that F prime of A is going to be approximately, right? I'm not saying it is delta X is 0. I'm just saying it's going to be approximately really small number, right? Now, some of that's small. What's small? Somebody say, oh, small is 20. I don't think so. Somebody say, oh, no, small is 0.1. Maybe small is 0.0001. It's kind of imprecise. But I'm going to say if we can, say small, I'm going to say this will be approximately this ratio over here. And then I can just manipulate a little bit, but it's delta X is not 0. It's small, but not 0. So I'm going to say delta X is not 0. Now, is that said in the problem? Yeah, basically over here, X2 can't be X1. All right, so let's write this down. So F prime of A delta X is approximately the same as F of A plus delta X minus F of A. But I know this to be something. This F of A plus delta X is actually just delta F, right? That's where this is coming from over here, all right? So I'm going to say for really small delta X, this is roughly true, all right? So then the question becomes is how do you do that, right? So the way to do that is to realize we're going to be using differentials to do that. Looks just like a differential, doesn't it? Where that delta F is really the differential dy. And what's a dy? Well, we just did the differential before, right? That's going to be F prime of X dx. But now I'm at the A problem over here. So I'm going to be looking at this thing here and putting this thing down as an equivalent statement. All right. All right. Let's talk about it. All right. This is going to get tough. We got to figure this out now. Well, I got the delta y written down again. They're using delta x over here. So I think the delta x, if I did that, that delta x now they're saying is the same thing as dx. Well, that's convenient because I know what delta x is. It's right over here. All right. That's not bad. We can do that. So we're letting this happen. Now, if that's sufficiently small, that's close to 0. What I mean by that, the A, wherever the A is, if the delta x is sufficiently close to it, it would be A minus, A sufficiently close, be close enough to 0. All right. So yeah, I'm kind of following along over here. And then I'm going to wonder, how do I get that, that dy thing? And basically what I'm doing over here is I'm just using this now. But now I know that delta x is what? Delta x. I got this over here. And remember this delta y, delta f, so to speak. I should say dy, I'm saying delta. Let's take a look at an example. All right. I'm not going to say it's going to be easy for you. Again, it's like you're reading something. So it says, find the difference between delta f at f prime a delta x. Well, I got to write this down. So what's delta f? That's going to be f of a plus delta x minus f of a. Well, let's take a look what they've got over here. And they said that the f of x, I'll write this over here now. I'm just reading. The f of x is going to be the cube root of x. I'm just reading it. I see that. And we're interested in the difference between, I got to write this down now, the difference between the cube root of 8.1 and the cube root of 8. They're interested in that difference. I got to look at this. I got to make sense out of it. And I got to write this over here. So delta F, that's a delta F. So it's going to be the cube root of 8 plus 0.1 minus the cube root of 8. Now, by the way, I'm not going to compute that. A computer's going to compute that. All right, we're going to put a computer, and we'll look at that later. So I want to make sure you understand what's over here. So what's the A? The A is 8. What's the delta X? Is 0.1. What's f of x? F of x is the cube root, or x to the 1/3 power. All right, let's see if we can handle it. Now, what did they do? I definitely wrote down delta f, but I have not written this down yet. So what we're saying over here is that the delta f should be approximately the same as f prime evaluated at a delta x. That's what we're claiming, right? But I say I'm not saying the same, approximately. So now it comes to a problem. I got to get f prime. What's that going to be? 1/3 x to the minus 2/3. And then I have to evaluate it at a. What's a? 8. That's going to be 1/3 x to the minus 2/3. What's x? It's 8. So it's going to be the cube root of 8. And we're going to square it. I think I can do it. Cube root of 8 is 2. 2 squared is 4. So it's be 1/12. Let's write this down. This is so much easier for me to compute. So this is going to be f prime of 8. What's delta x? Well, I just did it. It's 0.1, which to me is 1/10. So f prime of 8, I compute to 1/12, right? Times 1/10. I can do this without a calculator. Is 1/120. All right. So I realize it's, I'm not the most pleasurable computation, but I could have done that. What I can't do is I can't do this. So I need to use a computer. However, I am claiming that this is approximately delta F. Approximately. So let me go through that. And I want to point out, I did do the approximate value. It's over here. Let me blow this up for you. This is 1/120. If you use a computer, you get this number here. You don't need to, though, by the way. And then I'm going to claim over here is, if I did this one over here, I want to tell you that 0.1 is not that far away from 8. So I'm expecting them to be relatively the same. All right. So here's the deal. I don't think I did the computation, though. I didn't do the computation. I got to do it. By the way, it's going to be approximately that number there. I'm going to go to my computer, and I should have written that down already, but let me just do another share. Let me clear the screen. And I'm going to compute that number now. So it's going to be, let's see, and you're going to find this strange. I got to use a decimal. So 8.0, otherwise Sage is not going to compute it. And again, don't feel like you have to use this computer system that I'm doing, but that's to the 1/3 minus 2. Oh, I'm sorry. I did the wrong computation. So that could be 0. It was 8.1. Sorry about that. And I'll write that down for you. And my thing over here. I'll go back to my whiteboard later. I got to write it down now. 0.008. 299. I can go back to it. Just give me a second to get back to my whiteboard now. And yes, we're encouraging you to also use technology. All right, so I want to point out I did. When I went to Sage, I did this on Sage. I didn't write the whole number down. But what I'm claiming over here, if you look at this number over here, roughly the same number. I mean, roughly the same number. Within a level of precision, that's pretty good. All right, 0.008, 3. It's really out to this place over here that they agree. All right, so I'm going to say it's really not bad that you can do that. Of course, when we start to go through examples, you're going to be confused. I'm not saying you're not going to be confused. What we're going to try to do is lift the fog of confusion. All right, lift the fog of confusion. So I'm going to say from this conversation over here, hopefully you're able to follow some of the things I stated. One is local linearizations, basically just an equation of a tangent line, using a local linearization to approximate the value of a function near the point where it's being linearized. That's the point of tangency, by the way. And then using a differential to approximate the delta f in the problem. What's the delta x? That's pretty simple. It's just the change in x in the problem. All right, we'll go to examples next, and hopefully things will become more clear to you. Thank you.